Okay, so good morning, all of you. Today, of course, we are having the colloquium, asset colloquium in the morning. For obvious reasons, our speaker is going to come. He is from the other side of the globe. So hence this change of timing. We have Mr. Sudarsan Sadasivuni going to talk on fusion of fully integrated analog machine learning classifier with electronic medical records for real-time prediction of sepsis onset. I will, of course, formally introduce today's speaker in a minute. But what really transpired me to send invitation to today's speaker is a graduate student from at the university at Buffalo State University of New York, and his work recently featured in Science Reports, and that attracted my attention. And I thought it will be nice to listen to him about his work and the work that straddles between VLSI and chip design and the applications in the medical domain. I think this is a fantastic combination of research topic. So hence we are here. And firstly, I would like to thank Sudarsan for agreeing to speak today on this forum. For him and for some of you who may not know what ASSET is for, ASSET is a forum essentially organizing talks like this at DI for ASSET stands for Advances in Science, Engineering and Technologies. It has been almost 40 years old, a forum which, as I said, mostly organizes talks related to instrumentation, electronics, medical software, similar fields. Sudarsan, as I said, is a doctoral student from University at Buffalo State University of New York in the School of Engineering and Applied Sciences. His advisor is Arindam Sanyal, an assistant professor in the School of Electrical, Computer and Energy Engineering at Arizona State University. Sudarsan received double masters from University at Buffalo in 2019 and also at the University of Houston at 2017 in the Department of Electrical Engineering. During masters at Houston, he worked on building machine learning models that determine the best parameters which affect myopia using infrared distance measuring sensors and predict the risk of myopia at the very early onset. So I'm sure he's going to develop on some of these his research findings today. His research interests include machine learning enabled continuous health monitoring systems for personalized healthcare, analog, just a second, mixed signal circuit design for in-memory computations, and machine learning algorithms for health monitoring applications and so on. So we can really look forward to very, very interesting talk today based on Sudarsan's work. And with those words, let us invite Sudarsan for his very interesting colloquium. Over to Sudarsan.
Thank you so much for the introduction. Let me start my presentation. My name is Sudarsan Sadasivuni, and today I'm going to present to you article titled Fusion of Fully Analog Machine Learning Classifier with Electronic Medical Records for Real-Time Prediction of Sepsis Onset. So in this work, we are actually trying to combine the information obtained from the ECG signals as well as that obtained from the EMR. EMR is nothing but the demographic data or the previous health habits, etc., of a user or a patient. And in this work, we work together, like myself, Sudarsan Sadasivuni. Monjoy Saha is one of our postdoc working with Professor Banerjee. And Neil Bhatia is a cardiologist from Emory University Hospital. So Emory University and Mayo Clinic are the two hospitals that usually provide us with data sets. So for that, we had to take some permissions from their IR internal revenue boards. And with those permissions, we can make use of the datasets because most of the personal information are all pretty risky data, so that no one really gives access to the personal information. So let's get into the presentation. So this is the agenda for today. I will briefly explain about myself, and then I will explain what the background behind the continuous health monitoring systems, and then what motivated us to do work in this area. And I will first explain few workflows where we first came up with a digital model, and then we went to a analog mixed signal model, and then we further optimized the analog mixed signal model to come up with the final good model to predict diseases from physiological signals. And conclusions, like I'll conclude some of my findings. And let's go with my educational background. So at first I started my journey in the United States in August 2016. And then I did my master's at University of Houston, and I did it in 3 semesters. So by the end of December 2017, I finished my master's, and then I started my PhD in University at Buffalo. But I actually started my research in August 2019 with my professor, Dr. Sanyal. And during this course, I worked as a graduate research associate in University of Houston, where we worked on biomedical applications as well, finding out the different factors or different features that affect myopia. Myopia is the short-sighted, short eyesight. So, what really affects our eyes is what my study is like. Even the diabetics come into play in that. So, those are some of the features that affect myopia. Is what we found during my findings, and that project that I did was actually a small part of a very large PhD project at that time, by being done by someone else. And in during my master's in UB, I also worked as a graduate research associate at Vanderbilt University, like a different university. And over there, we worked on social media analysis mostly. And during my PhD last summer in 2021, I worked as a research intern for machine learning to FutureBee Technologies. And over there, I developed autoencoders that I used to estimate the channel state information. And our net goal was to reduce the compression factor, as in look at the performance of the channel state collection, even in the presence of noise, because in real time there will be large noise. So they wanted to bring in the application of machine learning or artificial intelligence into that. So that was pretty much, the beginning stages of their work. So that's where I started like last summer. And in my PhD, I have been working on developing ML models, like the healthcare applications, and then the algorithms for different medical applications. And I learned mixed signal designing during my PhD, and then I came up with two working papers, and two others are being done. That's my background. So this is the background of the heart diseases. So most of the deaths recently in the world are because of cardiovascular diseases. So in cardiovascular diseases, there will be multiple diseases coming into play, like heart attack, stroke, or heart failure, or even atrial fibrillation. So all these together, they fall under International Code of Diseases (ICDs), and we have multiple ICDs ranging from around I-20 to I-73, in which we deal with cardiovascular diseases and mostly heart-related diseases. Along with heart-related diseases, we also deal with the brain-related diseases, cerebral strokes, etc. So according to WHO, they mentioned that in 2019, at least 32% of the net global deaths are because of cardiovascular diseases, and most of them are because of stroke and heart attacks. So the only way we can, help people out or improve this condition is by having a continuous at-home monitoring. Because as a user, I can't go to a hospital daily to check if I'm sick. So I need some other ways, like even at home, even while I'm working or walking, I need to know that if I'm healthy or if I'm sick. So that was the main goal for the development of these continuous health monitoring devices in the world, across the world. And in this table, you can see the number of people who are being died because of the CVD and the cardiovascular diseases, and the total number of patients being admitted into hospitals because of multiple diseases. And most of the diseases the maximum percentage of diseases affecting death is actually CVD, as I mentioned already. There is the tabular data which is shared by WHO, World Health Organization. They usually share the statistics once every 2 years, because last year it's because of COVID. So the CVD doesn't really play an effect, because the highest number of deaths is because of COVID in the year 2020 and 2021. And in this study, what we were seeing is the increase in the number of patients having atrial fibrillation. Atrial fibrillation is a condition where the atria of the heart, atria is a part of the heart, where the atria has fluctuating flutters, like irregular beats suddenly. So that causes the heart to um, not perform properly. So in that cases, there is a high chance of getting heart stroke or a failure of heart. And the CDC did a study along the uh, 2 decades from 1998 to 2020, and they found out that the total number of patients having these diseases are actually increasing by a large number. So that also brought us to a conclusion that uh, many of the people's many of the people in United States are also being suffered because of the heart diseases. And this is the sepsis study. So sepsis is actually not just related to heart disease. It's a kind of infection that is caused if your internal organs are exposed to the atmosphere. So as soon as some person gets operated surgery, so he's put in ICU, and the clinical expert, I mean clinical expert, or the technician, he looks into the patient when he's in ICU and takes care of him. So during that, if there is some infection and internal organs of the body gets destroyed, at that time we can find that sepsis is a disease. I mean, at that time we can find sepsis being occurred. So the main goal over here is to find out the time before. Before a person going into sepsis, they should find out, because once a person goes into sepsis, it's really very difficult to bring him back, or to treat him. So in the study we see that if a patient, the total number of patients who got sepsis when in the hospital is way too less when compared to the total number of patients who get sepsis outside the hospital, like anywhere else other than the clinical setting. They are actually going into the sepsis state. So for again, the only way we can tackle this is by again looking into the early detection of sepsis. And to early detect the sepsis, we need to go through the continuous health monitoring again. So these are some of the reasons why we wanted to work on continuous health monitoring. And also in this study, you can see that this is one of the survey that I did across all the conferences and journals that published papers related to healthcare and system on chip, which is like continuous health monitoring. So we see that as the year is progressing, people and the total number of papers being published are increasing. That means the research in this field is actually starting to improve, because eventually everyone wants to come up with a good way to predict diseases, or a good way to stop people from getting very high diseases or dying early, etc. And eventually, these days, people are also working on predicting Alzheimer's diseases, the genes in Alzheimer's, even before the person is born, like even when he's inside a person. Like inside the egg itself, they're trying to see if a baby is having an Alzheimer's gene. So in this way, everyone wants to come up with a way to predict diseases instead of treating them. And these are some of the journals that I went through. So this is a lot of literature survey for the healthcare system on chips. And in this, we can see what a continuous health monitoring system is and how it's being used. So imagine this is the user. So there is a patch where the chip is going inside the body to get the ECG waves, because the sensor has to take the ECG wave. And one, not just the ECG wave, it's physiological signals. So it can be even EMG, EEG, EKG, ECG, same. So any kind of physiological signal. So they have the sensors, and once the sensors are taking the data, it should be in a position to make some conclusions. So in conventional methods, what they used to do is transmit the entire physiological signal. Like in the recent Apple Watch 7 series, what they do is they have a watch, and along with the watch, they try to come up with ECG sensors, and through the ECG sensors, they transmit the ECG waves to the mobile phone, and then on the mobile phone you can look into the ECG waves. This is the way they are doing the continuous health monitoring in recent Apple watches, and this is the motivation behind the work. So eventually, the wearable sensor, it transmits the ECG wave completely to the remote server, a mobile phone, or a desktop like a cloud AI, where they can do some analysis and predict some diseases. But the main issue with this is the transmission energy. So the transmission energy is too huge. It is in the range of 100 microjoule to 10 millijoules. So to reduce this, what we proposed is having an AI sensor right at the sensor node, having a AI block right to the sensor node. So over here we propose this model where there is a sensor, and sensor gets the signal processing, and then the signal processing is nothing but filtering and removing the noises in the physiological signals, and then extracting features. Once they extract features, they come up with a model like ANN, RNN, any ML model, and then they have a ADC to transmit the analog output into to some remote server. And once they transmit this output, instead of transmitting the whole ECG signal, the net power reduces by a large amount. So once these signals get transmitted here, you can look in this model where we have a EMG model saved in this remote server. Here we are using a mobile phone as an example, and we will input data, EMR data, as in the patient's age or the race, demographics, etc. And the ANN prediction scores and the MR data prediction scores are used as features to the Fusion AI model. And then they predict the net outcome as if the person is having some disease or they are fine. This is the net architecture that we were trying to build. I mean, that we built.
So let's ask you a question. In the previous slide,
sure.
so what is the power source? Maybe I missed it. What is the power source of the chip?
You mean the power source for the chip, like how we are powering the chip?
Yeah.
I mean, we usually give the DC supplies from outside, like 1.2 volt.
No. Since you said it is a wearable sensor, so just wondering whether it is inbuilt on the chip, or I mean, it has to be obviously something self-contained, or is it?
Oh, I mean, our goal was not to put it on wearable yet. Our goal is to do the chip part only. Okay. So we give power supply from outside.
All right. Okay. So right now it is not exactly wearable sensor.
Yeah, it's not wearable sensor. It is just a wearable AI block. I mean, we can embed it to the chip, but as of now, we didn't do the wearable part.
Got it. Okay.
Yeah, I mean, I have a working example of how it works in further slides.
Sure.
And in this slide, we can see how the power consumption of the wireless transmission is taking place. So the first raw ECG signal transmission. So if we transmit just the raw ECG, the power consumption is pretty huge. So it is approximately in 100,000 millijoules. So this is like impossible for a chip to handle. And even when compressed ECG gets transmitted, the power consumption is huge. Then people came up with a method where instead of transmitting ECG or the compressed ECG, they started transmitting the features of the ECG signal. So then the power started reducing. So we wanted to make use of this method And instead of sending the features, we wanted to just send the prediction scores. I mean, we wanted to transmit just the prediction scores by even placing a AI block to the sensor. So that was the net goal of our project. And to do that, at first we wanted to try different methods, like not just coming up with an analog model, because the state of the art usually uses digital blocks. So at first we came up with a method where we tried to use a digital recurrent neural network. And for LSTM, there is no need of feature extraction because it takes in raw ECG signal, and with the raw ECG signal, it makes some decisions. So in here, this is the architecture that we used. A raw IC signal goes through a stacked LSTM layers. So at first we have a LSTM layer of 30 cells, and then a dropout layer to reduce the overfitting, and then another LSTM layer and a dropout layer to reduce the overfitting because of this LSTM layer, and then a fully connected layer, which is used as a MLP and a regular ANN model, and then a softmax layer to come up with the prediction activation functions. I mean, this is a activation function area. So the net prediction score comes out. This is the proposed architecture. And we designed this in chip. This is the circuit level of the LSTM architecture that we designed. So over here, we came up with a model where we used the 65 nanometer CMOS technology. I mean, how we did this was we did mostly the model sim in MATLAB. And once we have a functioning model, we use the HDL coder. And using the HDL coder, it generated the Verilog code for each block. And once we have a Verilog code, if we give it to the Cadence Innovus and Genus tools, it will generate us the RTL to GDS as well as the layout, including the place and route system, because these days everything is automated already. So once we have this, we found out that the layout is occupying an area of 7.3 square millimeter. This is too huge for a chip because usually the electronic chip should be approximately 2 square millimeter, 3 square millimeter, etc. But 7.3 is like too huge. And that too, 87% of this area is occupied by the memory cells of LSTM. So, so we wanted to look further and reduce that. And these are the results of the digital LSTM model. The accuracy, I mean, we are trying to predict atrial fibrillation here. So when we use the PhysioNet challenge dataset, which is from 2017, we found that on that dataset, accuracy is 85.7 on the digital chip, and then the precision is 0.85, F1 score of 0.82, and recall of 0.82. In their, I mean, that's a challenge. So in the challenge, the best reported F1 score is 0.83, and our digital chip is giving a 0.82. So it's working pretty good. And we didn't compare it with the other F1 scores because they have different way of approach because they didn't directly use the ECG signal. They further compressed the ECG signal, and those ECG signals, compressed ECG signal is what they used for further analysis. So we didn't use them. And in digital circuits, we compared our work with the energy consumption. And in the previous solid state circuit conferences, we found two papers working on the similar dataset. I mean, same dataset, and they used a SVM model and multi-layer perceptron, which is nothing but a fully connected layer. And they are consuming an energy of 186 nanojoule and 330 nanojoule. And they are using design technologies of 90 nanometer, 65 nanometer. And we used RNN LSTM. We are consuming 21.8 nanojoule. So now, what are the disadvantages? The main disadvantage here is it is occupying 7.5 square millimeter of area. So it is pretty difficult or impossible to fabricate it and commercialize it because 7.3 square millimeter size of a chip would be almost a size of a half a finger. So it's not really a chip or a good model. So we wanted to reduce it. And in order to reduce it, we found the next idea is to do feature extraction and come up with ANN model or random forest model or SVM model, etc. So for that reason, we went with feature extraction methods. And to extract features on ECG signals, there are multiple ways where time domain features, frequency domain features, or the time plus frequency domain features, etc. And in the work we did, one of our published papers, we saw that using time domain features and in the same data set, we are actually able to get better accuracy than using time plus frequency data sets. So then we decided, in terms of accuracies, we decided time domain features are good enough, but that is not sufficient. So we wanted to look at how the hardware feature extraction looks. And for that, we further developed that study, and we came up with different digital blocks for each feature. And once we have the features, we computed the total area, and we saw for the time domain features, the area is approximately 98,163 square micrometer, and the power consumption is 11.8 milliwatt. So these are pretty good. But when we looked at the frequency domain features, it is having 81.92 square micrometer, which is like approximately 90 times larger than the time domain features. So we decided that it is not feasible, or it's not desirable to have a frequency domain features. So we just went with time domain feature extraction using this work. And that those are some of the conclusions, like to reduce the power, because our goal is to reduce the power and reduce the size. So to do the both, we have to use time domain features, because computation of FFTs is taking large area, and it is consuming too much power. So we want to avoid that, and we decided to move on with time domain features. Now, before moving on to analog mixed signal models, we wanted to give one more try with a digital artificial neural network. So with the extracted 63 time domain features, we tried to come up with a artificial neural network, and we see that the energy consumption is 72.2 nanojoule per classification. Although the size reduced by large, like the size of the digital ANN is point 0.8 square millimeter. I didn't report it here, but it's 0.8 square millimeter. And energy consumption is too huge. If you remember, LSTM is consuming 21.6 nanojoule, and this is consuming 72.2 nanojoule. Although the accuracies are pretty good, but the energy consumption is 3.6 times larger than the digital LSTM. So we wanted to see, since the area reduced, we wanted to move on and see how the analog mixed signal works for the power energy consumption, because we have more grip and more freedom while doing a layout with analog components rather than a digital components. And then we came up with a model which uses analog mixed signal ANN. And here we have a digital feature extractor. This is the feature extractor. And once we have a digital feature extractor, since our ANN block is analog, we had to use a digital to analog converter to convert the digital outputs of the feature extractor to analog, so that it goes as input to the ANN model. And once we have once we have an analog input, we will have an output, which is the output prediction. And then we have a comparator where the output prediction score is compared with the threshold. And if the output prediction is less than threshold, it has sepsis. That particular segment has sepsis, or it doesn't have sepsis. And the area is 1.67 square millimeter. So the area is pretty good. And we are using analog mixed signal, not just the digital now. And we observed that it is consuming only 12.9 nanojoule of energy per classification. So this reduced from digital ANN by approximately 5.4 times. And so using analog mixed signal, we are able to come up with both good accuracies, 98.84, reduced energy consumption, and lower area. These are the three goals, and our model was able to achieve it. And similarly, we tried the same thing to predict sepsis 4 hours before onset, and we got an accuracy of 91.1. So now the disadvantage with this process is we used 63 time domain features extraction. So for a feature extractor to be synthesized for 63 time domain features, it is very difficult to come up with a digital optimized place and route layout. So we wanted to reduce the features, but also improve the prediction accuracy. Accuracy shouldn't fall, but the features should reduce. For that reason, we came up with a algorithm which uses the fusion of ECG data and the MR data, which is the electronic medical records. And now I'll just go briefly about how we studied the ECG signals. So some of the noises associated with ECG signals are baseline wander, power line interference, and electrode motion artifacts. And since we try to come up with just time domain features, the major noise that we have to deal is a baseline wander. And to remove this noise, we tried three different filters. And in this, using high pass filter and moving average filter, we see that the signals characteristics or the information is changed using IR high pass filter, and using moving average filter, it is not changed. But these all are like having multiple components of filters to reduce the noise. Instead of that, what I proposed was a new method called median subtraction. So in this, we see that the signal information is not modified. I will explain it in the next slide how it appears. Yeah. So in this, you can see what baseline water is. So because we need a time domain features, it is all based on the peaks of the R peaks, which is nothing but R wave. So to come up with a algorithm to find these peaks, we need to use some thresholding value, and to come up with that thresholding good value, every wave should be of the same baseline. So my goal was to bring everything to zero. And to do that, what I did was, instead of taking this 1,000 samples at once, I collected 100 samples at once and computed the median of those 100 samples, and subtracted that median from all the 100 samples. So eventually our line, the baseline or the median is nothing but the highest times a particular value gets repeated. So when we subtract this, our median will change to zero. So once it is zero, that means our signal goes and stands at a point zero. And then we have a baseline of zero. And then we can use the thresholding method to find out the exact peak points and the peak values, because all my features are based on the locations of these peaks and the amplitudes of the peaks. And since this is sepsis data set,
Sudarshan, if I can ask a question. So in the previous
sure.
baseline restorer kind of thing, do you, there will be some very fine, tiny or whatever, insignificant amount of amplitude deficient on the peaks that you are looking at. Of course, it depends on the frequency of the signals and also the amplitude of the signals. So did you find some deficit or not? I mean,
Yeah, I mean, there'll be a small
that is negligible.
change. Yeah, that was negligible. That was the thing we found out through PSD, power spectral density. It said that the information shared by that net ECG is not modified because of the power spectral density.
Ah, okay. This is the column. Nice.
Yeah.
Yeah.
So in that way, we came to a conclusion that our signal is not losing any information, and it is still good to go and compute the features. In this, you can see how a prediction window is coming out. So for every patient, there will be a different onset time, sepsis onset. And suppose if you want to come up with a way to find out sepsis 1 hour before the onset, you take this onset point and go 1 hour away from this. And over there, we collect a 30-second window size. And that is the point which we say is 1 hour segment. So from there till sepsis onset, we need the ECG waves to say that they are all sepsis, because that is all during the 1 hour window. And in this way, we collected window and the data for sepsis. And non-sepsis is just a regular data because he doesn't have any disease, so it's all normal ECGs. And to come up with a feature extractor, we need to know the number of bits of the feature extractor. So then we did the bit resolution process and found out that for 4-bit, the accuracy is highest. We needed this because we wanted to see what is the total bits required to come up with a digital to analog converter. So since the 4 is giving high accuracy, we used a 4-bit capacitive DAX. And for time frame, so from sepsis onset, if we go on increasing the time, we see that the accuracy keeps reducing. And now the accuracy is 73.4 and it is 91.4 if it is 1 hour prediction. And this is using just the ECG signals. And in this, you can see the feature extraction hardware layout. In this, it gives out 14 time domain features. And the 14 time domain features are mean, median, max, min, and standard deviation of complete ECG segment. And also the similar statistics for the NN intervals and the ratio of standard deviation to mean of NN intervals, mean, median, and standard deviation of the RPs, which is the amplitudes, and the last is average heart rate. So to see that our feature extraction is good, we need to look at the last feature because if our heart rates are not in the range that we wanted it to be, I mean, are not in the normal range, that means the way we are doing feature extraction is wrong. So usually everyone who works on ECG try to come up with a heart rate feature because that's the only feature that can convey us that the process of feature extraction is correct. So in our work, we saw that the average heart rate is between 85 beats per minute to 125 beats per minute. And in this way, we try to have a hardware software co-design methodology. So what it means is we need our hardware model to be working similar to the software model. And for that reason, only thing that changes here is our software model training is similarly done, like having a NN model. So first we take the features extracted and then normalize them to be in a range, mostly 0 to 1 or -1 to 1. And once we have normalized the features, we try to train our NN model. And to train this NN model, we usually introduce a nonlinearity. In this case, we used a tanh activation function. So the software model is exactly trained in the same way, but to keep it similar to the hardware, what we had to do is in hardware, we design a differential amplifier whose response is similar to tanh. So that response we fit into a curve, and then that curve is given as an activation function to the software model instead of an ideal tanh. So now our software model is trained using the non-ideal response of the circuit. And then we get the weights, corresponding weights. Those weights we take and we hardly encode to our NN model. And to hardly encode, we have multiple ways of doing it. Either we can use the SRAM in memory computation or the switched capacitor in memory computation. The only disadvantage, I mean, we use the switched capacitor in memory computation. The only disadvantage with this over SRAM is the weights are hardly encoded. So the once we have a chip, it is having the exact weights and we can't change the weights. They can't be reprogrammed. And advantages of switched capacitor IMC over SRAM based IMC is there is no requirement of ADCs, and then the way the drain to source current is changing is nonlinear. But over here, the process of computation, which is charge compensation Q is equal to CV, that process is very highly linear. So there is no chance of missing a particular product, etc. So for that reason, we went with switched capacitors. Only disadvantage, as mentioned, is it cannot be reprogrammed. And these are the circuits that we use for our hidden neurons. So in this hidden neuron, we have a differential amplifier whose response is similar to tanh. And these are the different switched capacitors. And in the switched capacitors, we have these capacitors. These capacitors acts as the weights of the feature. So if you have a feature weight of 2, we will place 2 unit caps over there in series. And similarly, if we have a unit weight of, sorry, if you have a weight of 8, you will place 8 unit caps, and the input voltage xp of 1, xp of 2, so on. These are the input feature voltages, and these voltages will be equal to input feature plus a common mode voltage, because for a differential amplifier eventually there will be a minus VCM for every feature added. So since this is a balanced, if we send a feature of value input feature plus VCM on positive side, we will send a common mode voltage on the negative side. So eventually at the end of positive, I mean plus minus, it will be a subtraction, and we will have a net output of input feature into the weight. In this way, we designed the hidden layer neurons, and this is the output layer. It is exactly similar, except that instead of having a tan edge, we are using a softmax. So we just remove the regeneration source resistors. And this is the layout of the new chip that we designed. Over here, we have a ADC, analog to digital converter. It is used to convert the analog ECG segment into 10-bit. And this 10-bit ADCs go send the 10 digital bits to the feature extractor. And using the 10 digital bits, the feature extractor converts 14 different time domain features. And here we have a 4-bit CDACs, capacitive digital to analog converters. And using this capacitive digital to analog converters, we use feedback capacitance over there, where we normalize the features to be in the range of 0 to 1 or 0 to 0.125, uh, anything that we require. In our case, we did it from 0 to 0.125 because the circuit components, we use a 65 nanometer design technology. They can only accept 1.2 volt, and the common voltage will be approximately 750 millivolt. So we have to make sure that the input features should be less than 0.45. So it can only be either 0 to 0.125 normalized or 0 to 0.25 normalized, 0.25 normalized. And in our case, we did the 0 to 0.125 normalization. And this is the NN block. So this is the first hidden layer, and then this is the second hidden layer. In this, we have two different operations. This predicts sepsis, these first 4 neurons, and this particular neuron predicts atrial fibrillation. So we have two different functionalities, and this is the shared first layer, shared memory. And this is the net layout of the second continuous health monitoring system, because it has all the blocks, and this is actually ready to be used on a wearable, because all you need is a ECG sensor in front of it, and the ECG sensor's output goes to the ADC, and then the ADC will be in a position to extract features and then come up with these digital to analog converters and then predictions, and then send the prediction values to the remote server for further analysis. This is the test setup that we have in the lab. So this is our PCB board, and this is the test chip that we have. And these are the NI DAG, which we used to send the inputs to the chip. And over here, we collect the outputs. And once we collect all the outputs, we try to look for the further analysis, because our outputs that we collect are the prediction scores that come out of the softmax layer. So using those prediction scores, we try to look at different ways, because sometimes due to the parasitic capacitance is introduced during the fabrication, the threshold, I mean the threshold voltage changes. So if threshold is not zero point 0.5, we need to find out the threshold, and then for every chip, the threshold changes a bit, very tiny bit, like 0.51 or 0.49, it goes in that range. So we need to find out the threshold, and then we can label the predictions. And once we have this, in here we try to optimize our parameters, where for feature extraction, we use a thresholding method. So in here we said if the peak is 30% of the maximum value, take it as a peak. I mean, consider that particular signal as a peak. And similarly, when we tried it for 10 to 90%, we saw that for 30% thresholding, the accuracy is pretty huge. And for NN architecture also, we did many simulations, and we came up with this model which uses 20 neurons in the first hidden layer and 6 neurons in the second hidden layer. And in this, we did a time before onset sepsis and training accuracy. We found that for usually people mostly work for 4 hours or 3 hours before sepsis onset. So that's the reason even we went with the state of the art for our comparison methods. And in this ECG segment size, we took the 30-second ECG segment to compute features. So instead of just coming up with a 30-second, we tried looking into different sizes of the window. And we found out that for 30-second window, this model is working good for the features extracted. So we went with using 30-second, which is 90,000 samples. And now looking into the electronic medical records, these are the different features that we use. The first is gender, race, ethnicity, age, and these are the total number of patients we have. 514 patients have sepsis, 451 are normal, they are healthy people. And again, we have the breakup of male and female. We wanted to see how male participants are affecting sepsis. Like, is the model going to be specifically important to a particular group? And also we went with the race, where we have different races of people, and ethnicity, Hispanic or non-Hispanic, unknown people. Unknown are mostly unreported. They don't usually tell out their race or ethnicity. And then age of the people, because we wanted to see how age is influencing sepsis or non-sepsis, I mean, or being normal. And then we tried to use these features and we changed them into categorical features. And once we have a categorical features, we did this label encoding. And then we trained different models to see which model works good. And we found out that for random forest, these data set is giving good accuracy of 76%. And now we wanted to improve our accuracy of prediction, because if you remember, it has 86.4% accuracy, but on chip, previously when we used 63 features, we were getting 91.1%. So to improve this 86 to 91, we came up with a method where we use this demographic data and sensor ECG data, and we train two different models. And the prediction scores from these two different models are used as features to the meta learner, and then a net final prediction is done. And that we try to see if that improves the prediction. And finally, we successfully checked that it is working good by fusing these two results. And these are the AUROC curves. So for different R predictions before onset, we found out that AUC curves are giving good values from 0.99 to 0.94 after fusion. And this is the baseline model, which is EMR value for 0.79. And these are the different results during the fusion. So for on-chip ANN, using just the 14 time domain features ECG model, we have for 4 hour 86% prediction accuracy. And our goal was to improve this 4 hour prediction accuracy to over 91%, because using 63 time domain features, we were able to get 91.1%. And using just the EMR model for random forest, we got a 76% accuracy. So the prediction scores from this model and this model are used to form another late fusion model. And in this meta classifier, we tried again 4 different models: the SVM, logistic regression, random forest, and neural network. And for 4 years, the setting one, it has just um, these 4 features that we discussed: gender, race, ethnicity, and age. But the setting 2, it has the patient's previous history, previous health history as well. So using this, we found out that for logistic regression, our accuracy is increasing to 93 from 86. So our net goal is achieved. We reduced the total number of features from 63 to 14, and we came up with a new late fusion model. And we also try to use a electronic medical record model. And using all these models, even if we reduce the total number of features, our energy consumption reduced to 9.1 nanojoule per classification, which is less than half of what it consumed for a 63 time domain feature ANN model. And then the prediction accuracy also increased. So in that way, we try to say that our goal is achieved. And this is one of the applications that we developed to come up with the prediction scores for the MR model. So over here, this is random. Patient's ID is not required. And patient's age, we can input them as we have bins. Uh, Imagine putting 28 years. So then gender male and race Asian, ethnic group non-Hispanic, reason for visit, yeah, reason for visit is one of the reason, like the additional feature. So reason for visit, you can put some, I mean, like we can just add there. So some reason of cough or etc. And then once we click start, it gives us the prediction score. If we might get sepsis before 4 hours or we might not get. And this was actually working good on even the unknown data. Like we tried it on ourselves, it was working good. And we compared our work with the state of the art models. And in the state of the art model, they were trying to come up with with ways to predict sepsis before 4 hours, 3 hours, 6 hours, 4 hours, 6 hours, 4 hours, 3 hours, 4 hours. And the accuracies are actually pretty good. And for this model, they have 99.8% accuracy. And 9R model was 93% accuracy. But advantage of our work over this work is we need not go to a clinical setting because this has 26 features from lab. Lab is like we have to go to a hospital and get ourselves some clinical tests. So whenever there is a zero on lab, that means we need not go anywhere. We can just do a continuous monitoring just by sitting at home. And using that, we can compare our results with other works because I mean, eventually our goal is to do this at home monitoring, not going to a clinical setup. In that way, we reduce the total number of features also. And in this, we came up with a fusion model, which increased the prediction to 93%. And these are the conclusions of my recent project, where we came up with a model that is consuming 7.6 nanojoule per inference instead of 20, instead of 14.6 for the 60-10 domain features and 21.1 for the digital LSTM and 76.4 for the digital ANN model. So this is too less energy consumption. And also we made use of the clock gating method, where once we don't have a usage of a particular block in the system, we just turn it off and we only on it when that particular part of the system is required. Like imagine running a NN model. So if your first hidden layer is working, second hidden layer and output layer can be turned off. Like it doesn't require any power to be given to them. So controlling this power by clocking them, we reduce the power consumption. In future, what we can do is, um, in this we use the analog to digital converter and then a digital to analog converter after extracting features. So doing this process, there is a chance for loss of information. So if there is a loss of information, the results that we are obtaining, they are not really uh, reliable. Like we need, I mean, it might lose some information which is very important. And that might say that I might have some sepsis or atrial fibrillation. So we can't lose this information. So in order to make sure that we don't lose information, we wanted to try a direct analog feature extraction method. And that is our next project that we were doing right now. And it is still ongoing process. Yeah, that's the end of the presentation. And I have a video of my work that I can share. One moment. Yeah, this is the test setup in our lab. So these are the chip, and in using the NIDAX, we gave inputs to the chip, and then so we are programming the potentiometers, and once all the potentiometers get programmed, they'll be ready to start predicting diseases. So in this window, we are showing how different patients give give predictions, and these are the threshold values. So for every patient, the threshold changes. In this way, we are able to find out if a patient can get sepsis or he's fine, or if he has to go to a doctor soon. We also tried this on real-time patients. It's working good. Yeah, that's it. Thank you so much.
Yeah, thank you, Sudarshan. This is extremely nice work, and I think it has far-reaching applications. I'm sure, of course, there are things to go, and you need to kind of look up some other gaps that are there before maybe things can become reality of actually implantable kind of sensors. So one question that I asked in the beginning was something related to that, but maybe if my colleagues or anybody on the Zoom or YouTube want to ask any questions. One question regarding the SCA that you mentioned about, and so if you are not able to kind of change the weights, which is in some way required for you to, if you want to do a dynamic performance enhancement of the system, but that would is that not a severe disadvantage of going with the SCA model?
Yeah, it is a severe disadvantage. Like that is one of the only disadvantage, but that is very big disadvantage but eventually it's mostly ASICs, so it is application specific, right? So we design it according to the requirement, and also ECG sensors, the amplitude of the outputs giving out of ECG sensor, their amplitudes change as the age changes because they deteriorate as well. They won't perform same way. So at that time, what happens is our model has to still work good. So for that reason, although our chip won't work anything good, but we can collect the outputs, and outside we can do some self-supervision methods and try to improve the prediction scores or the model, because that was one of the disadvantages we found, that eventually after a few years, the sensor stops working good.
Yes. Yeah.
So the weights so the weights of the model should be changed.
Correct. Yeah, that becomes a very important feature of the chip, especially in biological sensors. I mean, it could be much more need for so. Yeah, but I think there could be many such developments, and I will also I liked your feature for clocking. To save the power, you want to kind of block one or the other sections. Clock gating, that is, I think, is a very important, very nice function, especially for wearable devices. So it's good, very nice work. Once again, I think I don't see any more questions. Of course, there were some compliments from the YouTube users about your good work, but there's no specific question per se. So once again, I would like to, on behalf of Asset Colloquium and TIFR in general, would like to thank for your excellent talk, and we wish you all the best for your PhD, of course, which seems just a foregone conclusion, but way beyond all your research interest in the future, and excellent career. Thank you very much.
Thank you so much.
Thanks. Bye.